Come on, it's actually done it. It actually does that. It goes your eye. All right, this is what you must know, okay? This is linked in the slideshow. I don't know what slide number that is, but if you've been paying attention, you probably know where it is. But last year we stopped right there, okay? I don't know if we even had all the rest of you on it. It's probably the same piece of paper as last year. I don't remember. But anyway, we stopped right there. We did 2, 3, and 4 region molecules. We're going to go back and explain what that means here in just a minute. But did we do 5 and 6?
I think we did.
We did do 5 and 6.
We did what?
We did not do 5 and 6.
I think we did.
Yeah, we talked about like how it.
We mentioned that they exist.
Yeah.
I swore we did.
I thought we
swore we did.
You think you failing? You said you scored.
I thought we did, but I don't know if we did or not.
Maybe we did.
That's not-
Sometimes I do, most times I don't. It just depends on which time I have, like, year to year. So maybe we did, but I don't.
I had very organized flashcards last year.
We'll dig them back
Yeah,
together.
we definitely did.
Oh, we have another test on them?
Yeah, I swear.
All right,
Yeah,
so
we never did
this,
definitely did
the
that.
rest of it, this year, it's all of it,
Yeah, no,
okay?
she know about hearing milk, yeah.
So we have 2, 3, and 4 region molecules, okay? But there is such a thing as 5 and 6 regions, and that involves expanded octets. You may have probably didn't mention that last year. There are certain elements on the periodic table who can have more than 8. We'll talk about who and why in the next day or so. But just as a heads up, this whole chart is fair game now, okay? All right, a couple of notes here, all right. This is a very important statement. If you can't draw the structure, this table is no good, okay? So the information on the table, the way you use the table is based off the regions of density and how many of those are lone pairs. So being able to count regions of density and number of lone pairs is how this table operates, okay? If you can't draw the structure correctly, then you don't have anything, you're counting everything wrong, all right? So, from yesterday, I think we left off with carbon dioxide, correct? So we had methane, ammonia, and water, correct?
Yes, sir.
All right, and that's through these papers. We followed a set of rules that are also on this same page that you can follow the link to. This set of, not really rules, it's a step-by-step process of how to draw these, right? We'll go through that on every one of these. All right, so to determine the electronic and molecular geometry, we need to count regions of density and numbers of lone pairs. So regions of density, we're counting around the central atom, all right? This one has 1, 2, 3, 4. All right? Easy enough? It's bonding pairs and lone pairs, okay? This one's got 1, 2, 3, 4. This one has 1, 2, 3, 4, all right?
Alive, Mr. Gill.
Yeah, we are. All right, so each of those have 4 regions of density, okay? So they are each tetrahedral in, let me scroll up a little bit. They're each tetrahedral in electronic geometry. All right, so each of them are tetrahedral. 4 regions of density, the electronic geometry is going to be tetrahedral, okay? but the molecular geometry will be different based off the number of lone pairs. Methane has 0 lone pairs, so it is also molecularly tetrahedral. Okay. Ammonia has 1 lone pair, so it is molecularly trigonal pyramidal, and water has 2 lone pairs, so it's bent. Okay. So from yesterday, I think we said this maybe we were going. The electronic geometry is the arrangement of the electrons. Okay. So how are the electrons geometrically spaced? That's the electronic geometry. How the atoms are spaced is the molecular geometry.
Okay, so.
Can you repeat with the molecular geometry?
How the atoms are spaced. So, if you have the same number of atoms as you have regions of density, like methane, then they're going to have the same geometries, tetrahedral, right? But if they're different, then they're going to be different, okay? So ammonia, take off an atom here, ammonia is still electronically tetrahedral, but molecularly it's trigonal pyramidal, okay? It makes a 3-sided pyramid. It's not flat, right? It doesn't sit flat. Okay. Water, take off another atom. Water is still electronically tetrahedral, but molecularly it's bent. Okay.
Well, that's why it's called. I never really understood why it was called that until like just now. Yeah, that makes sense now.
No matter when we get it, as long as we get it. Yep.
Okay, so let's just say that you didn't like have this chart like on, let's just say that you didn't have the chart and you look at it, like if you just look at it real hard, would you like kind of like figure out how it would be like you just like look at it, could you like kind of like figure out like you see how NH3 you have a whole pair, right? Like I know the electronics and molecular, you can look at it and be like instead of because it has 4 regions of electron density. But I'm saying like you see how you got that right there? Like is there like a way you could just like imagine it and be like, I know what that is. Like I know what that is.
Actually,
Can I learn
yes,
that
there
way?
is.
Can I
Here's
learn
how
that?
you do it.
Okay.
Okay. You have to go home. You have to make a model.
Okay.
I don't recommend spending $100 for these.
She'll do
toys, okay? I
I'll
recommend
get it thrift store.
marshmallows. No, they don't have these.
Just keep going. Just keep going. Forget it. Just keep going. Forget it.
Like cocaine-laced socks in the thrift store. You're not going to get a molecular model kit.
I had this whole outfit came from the thrift store yesterday.
Yeah, it's probably got fentanyl laced in it
Probably,
somewhere,
yeah.
you know,
I'm probably
bring
never
it
gonna wear
to
that.
you. Yeah. All right, so marshmallows, toothpicks, gumdrops work pretty well, okay? You need to make models, okay, because there's, not to get into all of the theory behind learning and all this stuff, but there's something about putting this in your hand and looking at it, okay?
Because like on the
Alone in a quiet room, and you just go, you know what?
Here's put marshmallows, toothpicks, and gumdrops together.
Yeah, and you know what, no, that's tetrahedral, and because that image right there will appear in your brain.
Like wouldn't that be better like on the test? Because like if you're on the AP test, you have this, like that's a lot of stuff to remember, and it's gonna be like we're gonna be like kind of like done, you know, with it. We're gonna be, we're gonna be on that.
We are in school, we're
I mean,
learning.
I know I'm talking about just like by the time like we'll already learn this, like we're on to something new, you know, like new. So like I'm just saying, like wouldn't it be like a lot better if you kind of just like automatically like yeah, okay, I got
Yes,
that.
you have to automatically be like that.
And we could, it'll be a little bit easier to be like that. We just did the marshmallows.
Yes. And then we're
That's
just
what I
saying,
do. That's all.
good,
what I
marshmallows,
do.
here we go, gumdrops.
Okay.
Don't
Can
choke.
you bring some for us to make models too?
See, like that was a good
Bring
question.
some
That was a
whole
good
class. There
conversation.
you go.
Yeah, we should all go study. We go study.
4 hours.
In the
So
library.
no, look, don't so recommend it. I would so recommend it. Go to the library, guys. The Jackson Library, and just be up there. It's so therapeutic. Like it's so peaceful. Like, I think, cause I went up there yesterday.
We're
allowed
Yeah, yeah, well, Eduardo went with me one time, but, I mean, he just walked in, like, he just walked in. He was like, he's like a basic white girl. Like, it was a stupid idea, I needed.
Y'all was
studying
studying
white
Spanish.
people. No, we were studying Spanish, we were studying Spanish. We were studying Spanish. Yeah.
So, everybody good?
But I just wanted to get that clarification.
We got it, we're clear, make a model, all right, good deal, excellent. All right, now, the rest of the how do you remember the angles? Okay, that's the trick. But the AP exam is usually not this specific, okay? So for example, with the tetrahedral, now we do need to remember this, if not for the AP exam, your college chemistry professional expects you to know that a true tetrahedral is 109.5 degrees. So we need to remember that number exactly.
So like all the way to
Yeah, so methane, for example, is 109.5 degrees. Okay? So a symmetrical tetrahedral molecule has a bond angle of 109.5 degrees. That's this angle right here.
Actually, remember that. Which angle?
This one, or either one.
So between the two molecules.
Yes. All right, now, how about the 107 and the 104.5? More than just, it would be great if we remember the exact numbers, but more important than the exact numbers is the fact that it gets less each time that we have a lone pair instead of an atom, okay? So when I take this atom off, okay, this tends to kind of so strange if you think about it, but a lone pair takes up more space than a bonding pair. A lone pair takes up more space than a bonding pair. Okay, so this lone pair takes up a lot of space up here, and it causes a repulsion, and these three atoms then get squeezed together slightly, which makes that angle now go from 109.5 to 107. Okay, so the lone pair causes a repulsion. They will ask you about this. Okay, so the lone pair causes a repulsion that squeezes those three atoms together. So the bond angle shrinks by about 2.5 degrees.
Okay.
Not a whole lot, but it's a little bit.
A lone pair causes a repulsion,
Causes an increased repulsion.
that would,
What does repulsion do? Just think about that.
that makes these go down.
Yes. If you have two lone pairs, you get even more of that repulsion. So this squeezes even further to about 104.5. So about a lone pair is worth about a 2.5 degree shrinking of that bond angle. But again, the actual numbers, they usually don't want the actual numbers. They usually accept a range, or maybe they don't even ask you about the numbers. But they're big on asking you, like, why is it smaller? Because a lone pair is more repulsive than a bonding pair. All right, so hybridization. What we have to do with hybridization is very, very simple. We just have to know the type of hybridization that exists in the central atom. The concept of hybridization gets very complicated. Okay, we don't have to go down that road. We do need to identify the type of hybridization. So it's equivalent to the number of regions of density. Okay, so this molecule has 4, right? That means an s orbital, one s orbital, and 3 p orbitals are going to hybridize. That's a total of 4, right? So I need an s and 3 p's to make a symmetrical 4-region molecule. So that's called sp3 hybridization. So anything that's electronically tetrahedral has sp3 hybridization around the central atom.
Can't we just remove that, like, the hybridization of is 1 less than region 15? That's how I would, yeah, I think that's how.
Could, but that's not gonna work too well when you combine the switcher. I don't think,
Because that, yeah,
I
that
remember the
works.
T-shape, I remember the T-shape.
I didn't say that.
The T-shape we got.
Off the
I
picture?
think we did six.
At least it
Well, I know we
was.
did five.
all right, let's
Still
see.
have the text.
Let's do carbon dioxide. This was a little different. All right, so I don't know where we left off yesterday, but let's go back to single bond and everything together. We're trying to place 16 electrons in this thing so that everybody has an octet, right? So what we ended up with was 2 double bonds between carbon and oxygen and 2 lone pairs on each oxygen, right? So that's 16 electrons and everybody has an octet. Okay? How many regions of density are around the central carbon? 2. So double bond counts as only 1 region. That's a confusing point. Okay? Double bonds and triple bonds count as 1 region of density. There are multiple bonds, but only 1 region of density. Okay? And then when we're talking about lone pairs here, we're only talking about the central atom. So we don't have any lone pairs on the central atom. We got some out here, the terminal atoms, but not the central. So this is 2 regions with no lone pairs, which is linear in both electronic and molecular geometry. A line is 180 degrees, and that's an sp hybridized. Okay. Good with that? Okay, now. So far, well, come on, let's go back to methane. This is symmetrical, right? Remember talking about that last year? Symmetrical. What if, I'm trying to find me another color here just a second. What if we make it unsymmetrical? There's a couple of ways we can do that. Where you add something to one side that's different from the other side. All right, so there's a couple of ways that this methane molecule could lose its symmetry. One is it could just not have this atom here, right? So we had a tetrahedral, not necessarily methane, this is not this is called methane. This is a tetrahedral shape, right? And it's symmetrical. If I take this off, like ammonia, it's not symmetrical anymore, correct? Right? It's got 3 and 0, right? There's nothing there. That's not symmetrical. So water's not symmetrical. Okay? Another way that we could make a tetrahedral molecule be asymmetrical is exchange a hydrogen for something else. Let's say that's a chlorine. Okay? So now it's not symmetrical. Right? Anytime you lose the symmetry, it's going to be polar. Okay? So that's what all this is saying. Okay? So linear is polar if the terminal atoms are different. So right here, this is linear. This is symmetrical, right? Okay? If I change this to a sulfur, let's say, which interchange pretty easily, okay? It loses the symmetry, now it becomes polar, right? So linear with the same terminal atoms is symmetrical and therefore non-polar. Lose the symmetry, it becomes polar. Same thing with trigonal planar. Okay, look back here, tetrahedral. If you have a tetrahedral molecule, it's polar if the 4 terminal atoms are different from each other. If they're the same, it's non-polar, right? The trigonopyramidal and bent are always polar. There's nothing about those shapes that can ever be anything but polar because they're just asymmetrical anyway, no matter if they're atoms of the same or not. All right. When they ask you about why this is polar, okay, you have to tell them it's because it's symmetrical or not. Okay, that's the word they want to know. So if they say Methane is nonpolar. Why? Okay, because it's symmetrical. If they say water is polar, why? Because it's not symmetrical. Okay? That's what they want. So symmetry is the word. Okay. Now, let's look at 5 and 6 regions. How much time do I have? All right.
15 minutes.
14 minutes. Okay, let's look at 5 regions first. Okay, a 5-region molecule looks like this. Okay, 5 regions. Okay. Where we at? Okay. All right, so this is a 5-region symmetrical molecule. Okay, it's got 5 bonding pairs, no lone pairs. This is trigonal bipyramidal. Okay, so all of the 5-region molecules have an electronic geometry that's trigonal bipyramidal. If it has 5 atoms, meaning no lone pairs, then the molecular geometry is trigonal bipyramidal. But what if it's got lone pairs? Okay, so this is kind of interesting because we've got all these fancy geometric names, but nobody could come up with one for this. Okay, so if you take one atom off of this, so that you have 5 regions, but 4 and but 1 lone pair, so 4 atoms, 1 lone pair, right? This is, instead of some fancy geometric term, it's called seesaw, because if you set it like that, it looks like a seesaw, which is like the most.
He's like.
It's like the most elementary thing that ever was. Like, I can only imagine like some chemist a long time ago made a model of this thing and set it on his desk. It was like, what am I going to call that? Like, I don't know what that is. He's thumbing through the geometry book. He can't find it. He's like, what is this thing? You know? It's probably like, seesaw. That's something big with 300 IQ, you know. That's what he came up with. That's seesaw. If you have 2 lone pairs, then it's T-shaped, right? Look at it like that, it looks like a T, okay? And then if you have 3 lone pairs, it would be linear. Now well, I'm off the wrong thing.
How do you know which one to take off? Or does it matter?
Well, it's going to rearrange itself. It's the way it's, all right, so let me get this right. Here we go. Okay. I think my T will look better this way too. All right, so that's seesaw. Okay, seesaw. And this is T. Okay. All right, and then it becomes linear. You take them off, right? Now again, the best way you're going to learn this is go home and make a model with this, with gumdrops all into it, clicks, right? Take them off, put them back on. About putting it in your hand, tactile learning. My wife, the kindergarten teacher, would call this using a bit. That means. Okay, so 5 regions. Now, if it's got 5 regions of density, it needs an S and 3 P's and a D because there's not 4 regions of P, right? Not 4 P orbitals. So let's use an example here of an expanded octet for just a second. Let's take sulfur, right? So all right, versus oxygen. Counter example here. Too many electrons. All right, so look at the difference in oxygen and sulfur. Oxygen's valence electrons are on the second energy level. There's no such thing as 2D, okay? But sulfurs are on the third energy level. It doesn't have any D electrons, but it does have a D orbital in that valence shell. So there is a D orbital out here, a 3D orbital. It's not being used. It can be used as an overflow space, okay? Just a place to put extra electrons. So any non-metal on rows 3 through 7 can expand its octet. If they ask you why, it's because it has extra D orbitals.
Only non-metal on rows
3 through 7 can expand their octet. If they ask why,
Wait. I mean, I'm trying to write fast here.
I know it.
Okay, now why? Go ahead.
The why is because they have empty D orbitals.
And we know that because of the hybridization.
We know that because we can draw orbital diagrams of them. We know the Aufbau principle, and we know that 1D and 2D don't exist.
I did say, okay, I did say the right thing. I did say the hybridization. Okay.
So,
Yeah.
to make a 5-region molecule, okay, to make a 5-region molecule, you'll need to hybridize 5 orbitals. Okay, that's an S, 3 P's, and a D. So that's called sp3d hybridization.
Oh, okay.
Okay. Again, not to dig too deep into hybridization, but basically what happens is these 5 orbitals form, and nobody really knows how this works. They form some kind of hybridization where you get 5 identical symmetrically shaped orbitals that are some kind of merged combination of sp and d. When and how that happens is, I don't think yet really understood.
Why did they decide the letters there and use their SP?
Don't know. I ask myself every year. We'll look that up. We'll figure that out.
Don't worry, I'll do it for you.
All right. Now, if you needed a 6-region molecule, then it would need to be. Change color one more time. A 6-region molecule would need an extra D, right? So this would be sp3d2 hybridized. It's a 6-region molecule. And it will look like this back here. One second.
The orbital names SP, D, and F stand for names given to groups of lines originally noted in the spectra of the alkali metals. Apparently, they stand for sharp, primary, diffuse, and fundamental.
That's how they said. I was like, what?
Interesting. Okay, so the 6-region molecules, okay, if you look back here, right, we'll do the first 2 and I'll scroll up, but the 6-region molecules, their electronic geometry is octahedral. Looks like this, okay, an octahedral, okay. If it's molecularly 6 atoms, then it's molecularly octahedral. All right, if you take one of them off, okay, it becomes what's called square pyramidal. It's a 4-sided pyramid looking thing, okay. If you take a third one off, the second one off, sorry, you have 2 lone pairs, it's going to be square planar. If you look back here at this again, this is the square and they're all in the same plane, right? It's a 4-sided object, 4 sides all in the same plane. It's a square planar. And if you take another one off, now you're back to a T shape. T's upside down. T shape. If you take another one off, it's back to what? Back to a line, right? Okay. All right, so you got to be sp3d2 hybridized, okay? And pretty much that's them, okay? So what's left to do now after today is to just practice. Practice drawing molecules and determining things about them from the drawing, okay? So we may.
It's a good
I think we
review.
briefly mentioned, because I know.
Probably
we
mentioned,
did-
I probably
know we
like,
did
hey,
the
here's
C-
5, here's 6.
Yeah, I think you mentioned them, but we were never
I
actually
may have.
tested.
I think I have to say all of them, but only which one.
I get to write new ones, and it'll help you remember better.
There you go. All right, any questions about all that?
Oh, it wasn't on the test.
Oh, yeah, here we go. Here's what we gotta do. Look. I almost forgot.
Uh,
Y'all gonna like this. Don't miss this. Should like it anyway. Well, where's the,
Are you looking for what? I don't want to ask.
hang on.
Oh, yeah.
Are you looking for the I'll look at those. Yeah, on the test when we did, on the test when we went, it really looked like 4. Yeah. I made quizzes for it. Hopefully I still remember, I really hope I remember the name. I don't, I'm a problem. Actually, let me see if I can pull it up. See, this is my quiz link to my best friend.
All right, remember this?
Oh, yeah.
Oh.
I love that.
I
Oh,
don't
sigma and pi bonds. We didn't talk about that. I'll take it in a second. That's easy. That's easy. All right, this quiz, what's today, Tuesday? Let's do this Thursday. Okay? So this is it. This is your quiz, same as last year. I give you this piece of paper to fill out. Okay?
Oh,
Just
we
like
did
this. I'm gonna make 12 copies of this and pass it out on Thursday. Okay? So, and here's why we need to know this so well. Okay? These molecules up here are very, very common on the AP exam. They use them for all kinds of examples of stuff. Okay? So we need to know their formulas, their structures, their geometry. This is molecular, by the way. Angles, hybridization, all this stuff. And on top of that, later on, you ought to know like their molar masses, especially their polarities. Like you ought to just know that. Okay? Like that's just such common chemistry knowledge. The second thing, the next layer to that is this, is that, for example, if we changed out methane, if we just changed out the hydrogen, let's say for 4 chlorines, okay? It's a different compound now, but its geometries and angles and hybrid polarity, it's all the same, okay? So if you memorize those 4 and then recognize on the test, hey, that's one of these 4 with one little change, right? Then you know all about that one, without taking the time to draw it all out and think about it. Because AP exam is quick, right? So having those 4 just memorized is going to speed your speed up a lot.
Is that the same one that we did last week?
Yeah, same one as last year.
Okay, because I literally just found that paper 3 days ago, and it's in my desk, so.
It's the same thing.
I need to start bringing my chemistry notebook from last year with me.
So what about sigma?
Let's talk about sigmas and pi's right quick, okay? All right, here we go. A single bond, single covalent bond, symbolized by a single line, right? That's a sigma bond, with Greek letter sigma, okay? A double bond, symbolized by 2 bars, right? That's a sigma bond and a pi bond.
Wait. Hold on a second. Yeah, I don't know
Pay attention to this now. A double bond is a sigma bond and a pi bond, with Greek letters, sigma and pi. A triple bond, which is symbolized by 3 bars, is a sigma and 2 pi's.
You're more of a sigma than you're sigma.
So, question.
Sorry.
Hang on, it's right here. Look, everybody look at this, quick examples, okay? Methane has 4 sigma bonds and no pi bonds. Ammonia has 3 sigma bonds and no pi bonds. Water has 2 sigma bonds and no pi bonds. Carbon dioxide has 2 sigmas and 2 pi's.
Well, wouldn't it be, like, how you did it, I got a question, like, for real. Cause on that double one, it's like, the sigma's at the first one, and the other sigma's at the second one, would it be one on?
What?
Just a triple bond.
That's what I'm saying.
What?
I'm looking at it like this, this one is at this one,
Uh-huh.
at this line, this one's at this line.
Uh-huh.
So I'm thinking that for one pi, one this, that's what I'm thinking, to be one pi. and one
That's a sigma. You don't know what the pi looks like. Pi is.
No, I don't know.
Double bond is it's two parts to double bond. One is a sigma and one is a pi. Oh, you gotta know.
Not all of them.
Just like, should it be one, so should it?
One makes two.
Yeah, one.
Makes two.
Oh. So one.
One plus one is two.
Okay.
It's been for a long time.
3 plus 3. Oh, I thought you said 3 plus 2.
And they're like, oh yeah, by the way, I went to like, and then